going to talk about mid-latitudes, where we live, weather system. So let's take a look at some of that today, see what we can find out from it. So what systems shape us? Well, key point, weather is basically controlled by air masses. It's where the change in air mass occurs that life gets interesting. That's where we have our bad weather. So air masses, as you can see here, can form in all different areas in relation to the United States. We have some that form over the cold Pacific, are called maritime polar air masses. We get the ones coming down out of Canada, the continental polar air masses. You might get one off the East Coast, maritime tropical air mass. You have varieties. And with that, where these meet is where all the interesting thing occurs. So think about it. Where they're meeting is along a front. So if you have a stationary front, that front's not moving. One side of it, you want to have cold air. One side is you want to have warm air. Well, we know warm air is always lighter than cold air. So the front is always going to slope towards the cold air. There'll always be warm air overriding it. So as you can see here, there's more clouds, more precip and stuff on the cold air side of the stationary front than there is on the warm air side. There may be some showers right along the front or just a little bit beyond it, but most of it will be on the cold air side. A warm front, basically all you're saying is the warm air is advancing. That's what makes that a warm front. Now you still have most of your precip along and ahead of that front, but along the immediate front where it's changing might be a little bit of clouds, maybe even a thunderstorm. Colder air, denser, the front is sharper sloped, so you're going more quickly. It's steeper, which means it's pushing the air up faster. So you get more intense precipitation typically with a strong cold front. And you can see here the different ways a cold front can move in. We do have backdoor cold fronts on the east coast of the United States. And they also occur out along the Rocky Mountains as well. Basically, it's what we think of, most cold fronts come out of the northwest. Backdoor cold fronts typically come out of the northeast. It's the only difference. It's still a cold front. An occluded front. What happens is, as the low is developing, an extratropical low, your typical everyday low pressure system, as it's developing, it is pushing that cold front forward fairly quickly, and that cold front overtakes the warm front. So it basically says, hey, I'm going to push all this warm air aloft because the warm air is lighter, less dense. So underneath it, it pushes that out of the way. And then there's a contrast between basically two cold air masses. And if it's a cold occlusion, the cold front that's moving in that occlusion is colder than the one ahead of it. That would be a cold occlusion. If it's warmer, that would be a warm occlusion. You get a lot of warm occlusions out on the Pacific, out along the west coast. East coast is more cold occlusions. And here you can see that. What they've done is literally push that warm air that was with the warm front aloft. So how do these extratropical cyclones, and remember, these are everyday cyclones. And on average, you'll get a cold front with some kind of extratropical cyclone passing your house every 3 to 5 days in the wintertime. So what happens is, well, you begin with a weak little low here where the develops along the front. There is divergence aloft. We've talked about that a lot. That's allowing the air to rise there, developing a low pressure system. Warm front out ahead of it, cold front along it. There is a temperature contrast right there. As that temperature contrast increases, the low intensifies. You've got a stronger warm front, stronger cold front. And at some point, you wind up with the beginning of the occlusion. And here you can see a long area of occluded front. So each one of these, the stronger the divergence aloft is, the more the convergence can occur at the surface. You think about it, convergence pulls air together. So what it's doing is increasing the contrast of temperatures, and you wind up with more and more wave shaped. And they're comma heads. They look like comma heads on satellite, these extratropical lows as they develop. They can get very circular, and they'll pull in dry air into them from the west behind it. Here you can see the conveyor belt. One of your questions this week might be talking about how a comma head forms. Well, you have the warm conveyor belt, warm air, lots of moisture probably, maybe even an atmospheric river with it coming up from the tropics somewhere. Out ahead of to the west of that, you have cold air coming in, and you probably, north of the low, you probably have a cold conveyor belt. Notice that the cold conveyor belt is moving to the west around the low, because remember the low is rotating counterclockwise, and you wind up with it at some point, though, it gets caught in the jet stream and moves back to the east or northeast. That's what forms the comma head. And there you can see the different types of precipitation that may occur. Think about it. If you're on the north side of that warm front, you're probably still in some cold air. You might be getting some freezing rain or snow as the warm air eventually moves in aloft, changes it over to rain, and you wind up with a rainstorm. Now, if the low goes to your east, you're probably going to wind up staying in that cold air. So you're going to get more snow. So that's one of the typical things that you're going to look at. Which side the location you're forecasting for is going to be in terms of that low pressure system. And here you can see numerous tracks of lows and how they're moving along here. And here you can actually see a weather map with how the snow is more concentrated to the northwest of the low. And you have basically a transition of precipitation to the northeast of the low many times. And they're cold core. These extratropical lows are cold core, so they get colder with aloft and more intense. You actually see, because the air is so dense with them, remember the pressure is going to drop faster, so you actually have deeper lows aloft with this kind of a system. Sometimes you get the non-occluded low, where the jet stream isn't as strong, maybe the divergence isn't as much, but you still get low pressures along it. A warm core cyclone or a thermal low might be when over the desert southwest, for example, gets very, very hot. What happens, that heat causes the air to rise, and we know there's less dense air at the surface. So that less dense air actually has lower pressure. Now, aloft, remember, as you're moving up with the density, because of that, the pressure is not dropping as fast. You actually get an anticyclone aloft. Whereas an extratropical low, you wind up with a low pressure aloft and very strong temperature contrast. Warm core cyclones, you do not. They do not have any temperature contrast with them, and it actually gets less and less intense as you go aloft. These also, we're going to talk about in a couple of weeks, tropical systems, and that is what a tropical system is like as well. So there are other regional little lake breezes, we call them, or sea breezes. We've discussed those somewhat. Lake Erie is the classic example. There are breezes along mountain chains. There are mountain and valley breezes. If you go into the mountains in West Virginia and say you have a big high pressure system, well, one side of the mountain gets heated before the other side, you're taking the temperature contrast, you're developing a wind circulation. Chinooks out on the west coast, wind coming down from the easterly wind down into Los Angeles, gets very dry as it's sinking, it's getting compressed, it's getting warmer. The same can happen on the east coast, east side of the Rockies as well, or even in the Appalachian Mountains. So with that, I just wanted to show you a couple really quick today's weather map. We have got low pressure, fairly decent low over Hudson Bay. See, coming into the area is a front. There's an actual stationary front down here to the south. Pretty good temperature contrast. Temperatures are in the 50s and 60s out ahead of this stuff. Temperatures are in the single digits to the other side. So that is a very strong front. If you were to look at it on satellite, you can actually see warm air moving up here. Got a good look at it with the infrared, fairly low, very moist. Higher clouds to the north, where you would expect that warm air has risen. And right along that boundary, then, if you want to look even more detail, you would think there would be some kind of a jet stream along there. Oh well, I lost it, what I had there. But there is a very strong jet right along this front. Actually, winds are gusting over 100 knots, 150 knots in this area right now. And the jet stream is always going to be on the cold side of the front. I hope you got a little bit out of this, and let me know if you have any questions.